When dealing with a metallic water pipe that is in direct contact with the earth for at least 10 feet, the primary function is to ensure electrical safety by providing a path for fault current to return to the source. This involves understanding the difference between a grounding electrode conductor and a bonding jumper, and when each is appropriately used. The water pipe, when meeting the 10-foot or more in ground contact requirement, serves as a grounding electrode. A grounding electrode is an object buried in the earth which establishes a direct electrical connection to the earth. Other examples are ground rods, ground plates, and concrete encased electrodes, often referred to as UFA grounds. The purpose of a grounding electrode is to stabilize voltage to earth during normal operation and to provide a low impedance path for fault current during abnormal conditions such as a ground fault. A grounding electrode conductor connects the grounding electrode to the electrical system, typically to the neutral bus in the service panel or to a grounding bus within the structure. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, based on NEC Table 250.66. Its purpose is to carry fault current from the electrical system to the grounding electrode, allowing the overcurrent protective device, such as a circuit breaker or fuse, to trip and clear the fault. A bonding jumper, on the other hand, is used to ensure electrical continuity between metallic parts that are likely to become energized. This could include metal water pipes, gas pipes, metal conduits, and other metallic components. The purpose of bonding is to create an electrically continuous path, minimizing voltage differences between these metallic parts. This reduces the risk of electric shock if someone were to come into contact with two or more of these metallic parts simultaneously. Bonding jumpers are sized according to NEC Table 250.102c1, based on the size of the circuit conductors that could energize the metallic parts. In the specific scenario of a water pipe that is 9 feet 11 inches in the dirt, it is treated differently than a water pipe with 10 feet or more of contact. Since it does not meet the 10-foot requirement to serve as a grounding electrode, it should be bonded. The bonding jumper connects the water pipe to the electrical system's grounding system, typically to the service equipment enclosure, the grounding electrode conductor, or the neutral bus. This ensures that the water pipe is at the same electrical potential as other grounded metallic parts, reducing the risk of shock. The code requires a grounding electrode system which includes a metal underground water pipe in direct contact with the earth for 10 feet or more. This grounding electrode system must be supplemented by an additional electrode, such as a ground rod or ground ring. This supplementary electrode is required to improve the overall effectiveness of the grounding system. The connection to the water pipe must be made within 5 feet of where the water pipe enters the building. The intention of this requirement is to ensure the connection is made on the supply side of any insulated joints or unions. Furthermore, the bonding jumper must be sized appropriately based on the size of the service entrance conductors, as specified in NEC Table 250.102c1. It is important to distinguish between the roles of a grounding electrode conductor and a bonding jumper. The grounding electrode conductor connects the grounding electrode to the electrical system, while the bonding jumper connects metallic parts to the grounding system to ensure electrical continuity. In the case of the water pipe with less than 10 feet of contact with the earth, the primary concern is bonding to minimize shock hazards. Here's a further clarification on the code requirements related to grounding and bonding of water pipes. The NEC Section 250.52.8.1 outlines the requirements for using a metal water pipe as a grounding electrode. It states that a metal underground water pipe in direct contact with the earth for 10 feet or more, including any metal well casing bonded to the pipe, shall be considered a grounding electrode. This means that if the water pipe meets the 10-foot requirement, it must be connected to the electrical system using a grounding electrode conductor. The grounding electrode conductor is sized according to NEC Table 250.66 and must be connected to the water pipe within 5 feet of its point of entrance to the building. Additionally, the water pipe grounding electrode must be supplemented by an additional grounding electrode, such as a ground rod or ground ring, as required by NEC Section 250.53. A. The purpose of the supplementary electrode is to provide an additional path to ground in case the water pipe becomes compromised or disconnected. Now, let's consider the case where the water pipe does not meet the 10-foot requirement for a grounding electrode. In this scenario, the water pipe is not considered a grounding electrode, and it should not be connected to the electrical system using a grounding electrode conductor. Instead, the water pipe must be bonded to the electrical system to ensure electrical continuity and minimize shock hazards. The bonding of the water pipe is covered in NEC section 250.104. A, which requires all metal water piping systems to be bonded to the service equipment enclosure, the grounding electrode conductor if of sufficient size, or to the one or more grounding electrodes used. The bonding jumper must be sized according to NEC table 250.102C1, based on the size of the circuit conductors that are likely to energize the piping system. The bonding connection must be made as close as practicable to the point of entrance of the water pipe into the building, and any insulated joints or sections of the water pipe must be bridged with a bonding jumper. It is also important to note that NEC section 250.104 B addresses the bonding of other metal piping systems, such as gas piping, that may be present in the building. These piping systems must also be bonded to the grounding system to minimize the risk of shock. In summary, the key difference between a grounding electrode conductor and a bonding jumper lies in their purpose and application. A grounding electrode conductor connects a grounding electrode to the electrical system, while a bonding jumper connects metallic parts to the grounding system to ensure electrical continuity. In the case of a water pipe, the decision to use a grounding electrode conductor or a bonding jumper depends on whether the pipe meets the 10-foot requirement for a grounding electrode. If it does, a grounding electrode conductor is required, along with a supplementary electrode. If it does not, a bonding jumper is required to ensure electrical safety. The correct application of grounding and bonding techniques is essential for ensuring the safety of electrical systems and minimizing the risk of electric shock. It is always recommended to consult with a qualified electrician to ensure that all grounding and bonding requirements are met in accordance with the NEC and local codes. Additionally, understanding the specific requirements of the NEC is crucial for anyone involved in electrical work. This includes not only electricians but also engineers, inspectors, and anyone else who works with electrical systems. By staying informed about the latest code requirements and best practices, professionals can help to ensure the safety and reliability of electrical systems for everyone. Grounding electrode conductors are sized based on the size of the service entrance conductors according to NEC table 250.66. For example, if the service entrance conductors are 2/0 AWG copper, then the grounding electrode conductor to a ground rod would be a minimum of 6 AWG copper. However, if connecting to a concrete encased electrode, a 4 AWG copper conductor is required. Bonding jumpers, sized per NEC table 250.102C1, are based on the size of the circuit conductor supplying the equipment being bonded. For instance, if a circuit is protected by a 20 amps breaker and uses 12 AWG copper conductors, the bonding jumper to a metallic enclosure would typically be 12 AWG copper as well. The purpose of bonding is to create a low impedance path for fault current, ensuring that overcurrent devices operate quickly to clear the fault. Improper grounding and bonding can lead to dangerous voltage on metal parts, increasing the risk of electric shock. It can also cause equipment malfunction and increase the likelihood of fire. Regular inspections of grounding and bonding systems are essential to ensure their integrity. These inspections should include visual checks for corrosion, loose connections, and damaged conductors. The electrical testing, such as impedance measurements, can also be performed to verify the effectiveness of the grounding and bonding system. When working on electrical systems, always follow safe work practices. This includes de-energizing circuits before working on them, using appropriate personal protective equipment, and following lockout/tagout procedures. Never assume that a circuit is de-energized, always test it to verify. If unsure about any aspect of electrical work, seek assistance from a qualified electrician. Non-metallic plumbing presents its own challenges and does not require bonding in the same way as metallic plumbing. However, other metallic components in the vicinity, such as metal supports or metal fixtures connected to the plumbing system, may still require bonding. The use of proper fittings and connectors is essential for ensuring reliable grounding and bonding connections. These fittings should be listed and labeled for their intended purpose and should be installed according to the manufacturer's instructions. Avoid using makeshift or unapproved fittings, as they may not provide adequate electrical conductivity. In some cases, it may be necessary to use exothermic welding, also known as a CAD weld, to create a permanent and reliable grounding or bonding connection. This process involves using a chemical reaction to melt and fuse the conductors together, creating a strong and corrosion-resistant connection. Exothermic welding is often used for grounding electrodes and for bonding large conductors. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. These devices divert the surge current to ground, preventing it from damaging sensitive electronic equipment. SPD should be installed at the service entrance and at other strategic locations throughout the electrical system. Proper grounding and bonding is essential for the effective operation of SPD. The grounding system provides a low impedance path for the surge current, allowing the SPD to divert the current safely to ground. Without proper grounding, the SPD may not be able to function correctly, and the surge current may still damage equipment. Ground fault circuit interrupters, or GFCIs, are designed to protect people from electric shock. These devices monitor the current flowing in a circuit and quickly interrupt the power if they detect a ground fault, which is a leakage of current to ground. GFCIs are required in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Proper grounding is essential for the effective operation of GFCIs. The grounding system provides a path for the fault current to flow, allowing the GFCI to detect the fault and interrupt the power. Without proper grounding, the GFCI may not be able to function correctly, and the risk of electric shock may be increased. Arc fault circuit interrupters, or FSIs, are designed to protect against fires caused by arcing faults in electrical wiring. These devices monitor the current flowing in a circuit and quickly interrupt the power if they detect an arcing fault, which is a dangerous condition that can cause a fire. FSIs are required in many locations throughout the home, such as bedrooms and living rooms. Proper grounding can help to reduce the risk of arcing faults. A well-grounded electrical system provides a stable reference point for the voltage, which can help to prevent voltage fluctuations that can lead to arcing. In addition to grounding and bonding, other electrical safety measures should be taken to protect against electric shock and fire hazards. These measures include using properly rated electrical equipment, avoiding overloading circuits, and keeping electrical equipment in good repair. It is also important to educate people about electrical safety and to teach them how to recognize and avoid electrical hazards. This can help to prevent accidents and injuries. Consider the scenario where a metal conduit is used to protect electrical wiring. The conduit must be properly bonded to the electrical system to ensure electrical continuity and minimize shock hazards. The bonding connection should be made at both ends of the conduit and at any intermediate points where the conduit is cut or spliced. The bonding jumper should be sized according to NEC Table 250.102C1, based on the size of the circuit conductors within the conduit. Another example involves a metal junction box used to connect electrical wires. The junction box must be properly grounded to the electrical system to provide a path for fault current. The grounding connection should be made to the grounding terminal inside the junction box, and the grounding conductor should be sized according to NEC Table 250.122 based on the size of the circuit conductors. In commercial and industrial settings, grounding and bonding requirements are often more stringent than in residential settings. This is due to the higher voltage levels and the greater potential for electrical hazards. In these settings, it is especially important to follow all applicable codes and standards and to consult with a qualified electrical engineer to ensure that the grounding and bonding system is properly designed and installed. Regular testing and maintenance of grounding and bonding systems are essential for ensuring their continued effectiveness. This includes visual inspections, continuity testing, and ground impedance measurements. Any problems or deficiencies that are identified should be corrected promptly. The NEC is updated every 3 years, and it is important to stay informed about the latest changes and revisions. These changes may affect grounding and bonding requirements, as well as other aspects of electrical safety. By staying up to date with the NEC, electrical professionals can ensure that they are following the latest best practices and providing the highest level of safety. Some local jurisdictions may have additional grounding and bonding requirements that go beyond the NEC. It is important to check with the local authorities to determine if there are any such requirements in your area. These local requirements may be based on local conditions or specific hazards that are present in the area. Improper grounding and bonding can have serious consequences, including electric shock, fire, and equipment damage. It is important to take grounding and bonding seriously and to follow all applicable codes and standards. By doing so, you can help to ensure the safety of people and property. Remember, when dealing with a water pipe that doesn't meet the 10-foot in-ground contact, bonding is the correct approach, ensuring electrical safety by equalizing potential.